You ever just listen to a killer guitar solo and wonder, what is actually happening right there? Well, it's not magic, it's pure physics. Believe it or not, all the music we love is built on this hidden world of waves, tension, and, well, resonance. So today we're going to pull back that curtain and take a look at the physics that makes music possible. All right, let's just jump right in with the big question. Think about a single guitar string. It looks so simple, right? But a musician can pull a whole symphony of different notes out of it, from a deep growl to a high-pitched scream. How? How is that even possible? The secret is all about how that string vibrates. It's not random. It's a very specific, beautiful pattern that we call a standing wave. So to really get how that string can sing, we have to decode the wave itself. We're going to start with the absolute fundamentals and build our way up. It's going to be fun, I promise. First step, the transverse wave. Okay, I know the name sounds a little technical, but the idea is super simple. Just imagine you're holding one end of a long rope. If you flick your wrist up and down, you see a wave travel down that rope, right? Well, think about it. The wave is moving away from you, horizontally, but any single piece of that rope is just moving up and down, vertically. That's it. That's a transverse wave. The motion of the rope is perpendicular to the motion of the wave. Okay, so what happens when that rope, or say a guitar string, is tied down at both ends? Well, this is where it gets really cool. A wave travels down the string, it hits the end, and then it bounces back. And when that original wave and the reflected wave interfere with each other just right, they create this amazing stable pattern, a standing wave. It looks like it's just vibrating in place. And you'll see these spots that don't move at all. Those are called nodes. And the spots that are vibrating like crazy, those are the antinodes. So you might be wondering, how fast is that wave actually moving along the string? Well, physics gives us this really clean, simple rule for it. The speed, which we call v, is just the square root of t over mu. Now, t is simply the tension, how tight the string is. And mu, that's the Greek letter mu, is what we call linear mass density. That's just a fancy way of saying how heavy or thick the string is. So here's the key takeaway. The speed of the wave really only depends on those two things, how tight you pull the string and how heavy it is. That's it. Now, that equation is a pretty bold claim. But in science, we don't just take things at face value. We have to test them. So let's see how scientists actually prove this relationship with a classic lab experiment. So the setup is actually pretty clever. You have a string that's hooked up to a little machine, a vibrator that just shakes it at a constant frequency. Then the string goes over a pulley, and on the other end, you hang some weights. That hanging mass is what provides the tension, T. So by adding or removing weights, we get to control the tension with incredible precision. So what's the game here? It's kind of like a treasure hunt. You're looking for the sweet spots, those perfect weights that make the string lock into a beautiful, stable standing wave. And every time you find one, you just count the number of antinodes, those vibrating loops, and write down the mass you used. Then you change the mass and you start hunting for the next pattern. So after you run the experiment, you're left with a table full of numbers. And just looking at it, it might not seem like much. But this is where the real science starts. It's time to find the story that's hiding inside that data. Okay, let's take a look at some sample data. You can see something kind of weird right away. As we get more antinodes, as we go from 3 loops up to 6, the amount of mass we need actually goes down. So to get more vibration, we needed less tension. So there's definitely a relationship here, but it's not a simple one. The question is, what is it exactly? So yeah, what is the secret? How do we take this jumble of numbers and turn it into something that makes sense, something that proves our theory? Well, it turns out there's a really simple, really elegant pattern hiding in there, but you have to know how to look for it. And here it is. This is the big aha moment. If you try to plot the mass versus the number of antinodes, you just get a weird curve. But, and get this, if you plot the mass versus 1 divided by the number of antinodes squared, boom, everything snaps into place. You get a perfect, beautiful, straight line. This is it. This is the proof that our theory was right all along. That hidden relationship was there, we just had to visualize the data in the right way. And what's so cool is that this line isn't just a pattern, it's packed with information. The slope of that line, you know how steep it is? That one number tells you almost everything about the physical setup. The string's density, its length, the frequency of the vibrator, it's all in there. And the y-intercept, where the line hits the vertical axis, that has a secret of its own. It actually tells you the mass of the little pan that was holding all the weights. It's just incredible. The physics of the entire experiment is encoded right there in that one simple line. Okay, this is all fascinating stuff for a physics lab for sure, but let's bring it back home. How does all this connect back to our guitarist and to the things we actually see and hear in the real world? First, we gotta clear up one super common point of confusion. The wave traveling on the guitar string is not the sound you hear. They're two totally different things. The wave on the string is a transverse wave, and its speed depends on tension and density. That vibration is the source. It pushes the air around it, and that creates a totally different wave, a longitudinal sound wave that travels through the air to your ear. So think of it like this. The string is the cause, and the sound is the effect. Two different waves. And just like that, we're back to the guitar, and we can finally answer our question. When a guitarist turns one of those tuning pegs, what are they doing? They're increasing the tension, T. That makes the wave travel faster along the string, which gives you a higher frequency, a higher note. And why are some strings thick and some thin? Well, that thick bass string has a really high linear density, mu. That makes the wave on it travel slower, giving you that deep, low note. It all comes back to that one simple equation. So let's wrap this up. We've seen that the note a string plays is all about its tension, its thickness, and its length. And we saw how a simple graph can uncover these really deep physical laws. Now, this brings me to a super important tip, whether you're writing a lab report or any kind of technical summary. Your conclusion needs to be strong. And a strong conclusion gives the result, not the process. Don't say, we did the experiment and plotted the data and found a linear relationship. No, get straight to the point. Say, the experiment confirms a direct, linear relationship between, you see the difference? You're not describing your journey, you're declaring your discovery. That's how you communicate like a scientist. So the physics of a simple vibrating string unlocks the secret code of music. It really makes you think, doesn't it? Now that you know how to look for these waves, what other things in your daily life can you start to explain? From the microwave that heats your food to the ripples spreading out in a puddle, these principles, they're absolutely everywhere.